So, indefinite integrals, what are they? If you'll recall from last time, the fundamental theorem of calculus part 2 says that if you want to evaluate a definite integral of f of x from a to b, then all it takes is to find any antiderivative of small f, capital F, and evaluate capital F at the upper and lower limits b and a, and subtract them, and you get the exact value of your integral. Right? And this tells me antiderivatives are going to play a really useful role in integration. So much so that we'd like to develop a consistent and a convenient way of talking about the antiderivative of a function, or to be more precise, the family of antiderivatives of a function. And that's what indefinite integrals are for. Definite integrals are those with numbers for the lower and the upper limit, a and b, while an indefinite integral is simply one without limits. Right? So you write the same symbol for the integral. You have a function inside. It's also called the integrand. dx tells you you're integrating with respect to x. You just don't have any numbers. And again, what this stands for is it's equal to capital F of x means capital F prime of x is equal to small f of x, right? So again, this means it's an antiderivative. And as I mentioned a while ago, to be more precise here, we will write plus a constant c beside capital F of x because of the fact that, remember, adding any constant to a function does not change what its derivative is equal to. Right? So I can have a plus 1, a plus 2, a plus 3, whatever. I take its derivative, it's still going to be small f of x in the end. And just to emphasize the distinction here between definite and indefinite integrals is that when you evaluate a definite integral, you're going to get a number which represents the area in between, right, f of x and the x-axis, that net area. Whereas for the indefinite integral, that's not a number, but instead it's a family of functions. Right? So even though the notations look really similar, right? One has upper and lower limits, one doesn't. They describe different objects in calculus, right? So just be careful about that. And well, here's a list of some common indefinite integrals, right? Or some common antiderivatives. And you will recognize all of them as simply the reverse of their corresponding differentiation rules. Right? So for instance, the derivative of sine is cosine, right? But when we write this in terms of an indefinite integral, we will say, well, the integral of cosine x is now sine x plus c. Right? Remember, we're just going the other way here. You're reversing differentiation when you're looking for an antiderivative. And so I encourage you to look and memorize this table of common integrals. And in fact, not just these ones, but there are other ones in our textbook that you should know. And I'll give you an example here. Right? Say you were asked to evaluate the indefinite integral of 6x squared minus x to the 4th power dx. Right? So this is, again, the same thing as asking can you find a function such that when you take its derivative, you get 6x squared minus x to the fourth power? And can you find the family of all these antiderivatives? So, well, we could look at the table of integrals that we saw here on this slide, seeing that, well, we actually have this general rule for taking the indefinite integral of x to the n, where n is not equal to minus 1. Right, so that's just the reverse of the power rule for differentiation, which says, well, if you take the derivative of x to the n plus 1, that's x to the n plus 1 raised times x raised to the n. But if we want just x to the n as the result here, you'd have to divide by n plus 1 instead. Right? So when the exponent goes down, they'll cancel each other out. So for 6x squared, what happens there? Well, x squared becomes x cubed divided by 3 when you take the antiderivative. What happens to 6? 6 is just there, right? Because of the same rule for differentiation, that when you have a constant multiplied by a function and you take the derivative, that's the same thing as taking the derivative first and then multiplying by that constant. It's the same for integration. Right, so we take the antiderivative of x squared, you get x cubed over 3, and you multiply by the constant 6. X to the fourth power is x to the fifth power divided by 5. And to be correct here, we will say plus c, because again, we are looking for the family of antiderivatives of your function. And it is basically all these functions for any value of c in the real numbers.